Hello there and welcome to the third video of the linear regression section. In this video we're going to cover the Python implementation for the linear regression model. We'll do this by working with the real Boston house prices dataset provided by the scikit-learn library. Based off of the features in this dataset, we're going to create a linear regression model that can predict house prices in the Boston area. A quick note, here's a link to the information and documentation for this Boston house prices dataset. There's some functionalities and information there, and if you're curious about that as we go through the walkthrough, or if you have any questions on those functionalities, you can refer to this link. So now, without further ado, let's go to the Google Colab and get started on linear regression with Python. The first thing we're going to do is our imports. So let's start off with import pandas as PD. One second, let me make it bigger. There you go. So it's import pandas as PD. Then we'll import numpy as np. And now we'll start with importing our visualization libraries. So we'll import matplotlib as plt. And then we'll import seaborn as sns. And in order to see these visualizations in our notebook environment, we need to specify with this line of code called matplotlib inline. So now that we've imported all the necessary libraries, we can now import our scikit-learn dataset. So we'll start by saying from sklearn.datasets import load_Boston. So this is the name of the dataset import. And now that let's do that, let's run this cell. Oops, I think I made a typo somewhere. Datasets, there you go. Oops, let me try that again. There you go. Cool, so now that we finished doing the imports, we can now actually load in the Boston house prices dataset, the actual data. So we'll do this by saying Boston equals load_Boston. So this load_Boston function is one of the functionalities that I mentioned is in the documentation for the scikit-learn dataset. So if you do have questions about that, you can refer to that link. So now we've loaded in the Boston dataset. Let's run this cell. Great. Now, an important thing to note is that this Boston value is going to be our dataset, right? And what the Boston variable is that it's a dictionary. So to briefly summarize, a dictionary is a data structure that contains key value pairs. And what these keys do is that they unlock certain aspects of our dictionary dataset. And I'll show you what that means as I go through the walkthrough. We can access these keys. It may sound a little bit confusing at first, but we can access these keys to our dataset using the you can use the .keys function. So basically, whenever you have a dictionary and you want a list of all of its keys, we can do that with this .keys function. And we can see this list by running this line of code here, and there you go. So this list contains all the keys that we can use to obtain certain aspects of our data set. So if we use this data key, we can get the actual data. If we use the target key, we can get the target values of our data set. If we use the feature_names key, we can get all the names of the feature columns. The description key here, I'm going to show that right now in a sec, can give us a description of our data set, and the file name will give the file name of the data set. So now that we have that out of the way, let's actually use the description key to get a better sense of all the characteristics, attributes, and features in our dataset. So basically, when you have a dictionary, you can get these certain aspects of the dictionary by doing dictionary.key. So in this case, we do boston.descr to get its description. There you go. So here is all the characteristics of our dataset. As you can see, this provides a summary of all the features in the dataset as well as the target value, which is called MEDV, or median value of owner-occupied homes in 1000s. So this is important because the values won't actually be in thousands of dollars. We're going to have to multiply all the target values by 1000 to get the actual price of the house value. And you'll see that as I show the data set. But pretty much you can read through all this attribute information. Some of the important ones to be aware of are per capita crime rate per town, the proportion of residential land zone for lots of 25,000 square feet, the proportion of non-retail businesses, acres per town, the average number of homes per dwelling, things like that. So you can read that. I won't cover all of them right now, but you can definitely refer to them if you forget what these acronyms stand for. So now that we've got a better sense of our data set, let's actually construct a pandas data frame of our data. So as it is right now, the data is a NumPy array. And I'll show you what that means in a sec. Pretty much the key to get our data is called data. And if we use Boston.data, we're just going to get a NumPy array for all the data values. But that's a little bit, but for ease of use, it's better to use pandas. And it's also good practice that we can work with the pandas data frame. So to create this data frame, let's do pd.dataframe boston.data, because that's going to be our data values, data points. And then our columns for this data frame is going to be the feature names. So we'll do boston.feature names. Cool. So now that we have this done, I think there's no typos. Let's run that. Great. So now that this has been constructed, let's get a visual of what this pandas data frame looks like. And we can do that by using the .head function. So pretty much what .head is allowing us to do is it allows you to see the first 5 data points of your data frame. And if we take a closer look, these columns are our feature columns, which our machine learning model will train on. And we're actually missing something. We're missing the target column. So to add that to our data frame, let's create a column for our target values called house_prices. And we can do this by saying df_boston house_prices. So we're creating this column and we're setting that equal to boston.target. If you remember, this key provides you all the target values, and we're creating a column for these target values. So this contains the prices of the Boston houses. So now that we have that, we can get a visual of our data frame again. We can see the data frame matrix. Oh, oops, I forgot to run this. There you go. So now, as you can see, we have our feature columns as well as the target column. Great. So now that we have our pandas data frame constructed, let's now look at the statistics, some visualizations, and some basic exploratory data analysis to get a better understanding of what our data exactly is. So we already know some of the attributes and characteristics of our data. So let's get a more technical understanding of it. We can do this by saying df_boston.info. This provides some information about your feature, the data within your the data types for your features. So these are the feature columns, and as you can see, all of the data types are float 64s. So this is good. That means all the data is numerical, and that's going to work really well for a linear regression model. Now that we understand that, we can get a quick account of statistical information of our data frame by using the .describe function. So let's do df_boston.describe. And what this does, if I run it, so as you can see, we can get some of the statistical information for each of our columns. The count, the mean, the standard deviation, the minimum, the percentiles, quartiles, and the maximum. So this is great if you just want to know the numbers and stats behind your data. I won't go too in depth with this. You can definitely look at it, see some of the counts, see the numbers. What are some differences between? What are some of the statistical differences between the various features? Things like that. So now that we have that out of the way, let's get a quick recap of all of our columns in our data set. And to do that, we can pass in df_boston dot columns. So if we run this function here, if we run this line of code here, you can see these are all of our columns. These are the names of our columns, and everything is set. So now we can move on to the plots and visualizations. For the first visualization, I won't actually run this, and I'll explain why in a sec. This visualization is the pair plot from Seaborn. And what it does is it creates histograms and correlation scatter plots, which allow you to see how different columns are correlated with each other. And to pass it in, what you would do is sns.pairplotdf_boston. So now, before you actually run this, I want to give a quick disclaimer. For the sake of time, I won't run this function because it may take a while for all the plots to load in since we have so many features in our data. So it's going to create a lot of histograms and correlation scatter plots. You can try it out if you're interested in seeing how this pair plot looks and works, but I wouldn't recommend it for this dataset in particular because it's so large. And the reason why large datasets don't really work with this sns.pairplot function is because for larger datasets with a lot of features like ours, it may take, like I said, it may take a while for it to run since there will be so many plots and histograms as the output. And so because there's going to be so many plots, the output of these plots is going to be really small. So it's going to be really hard to actually see like all the details in these visualizations and plots. And it's going to be fairly difficult to actually interpret them and make any sense of the data that's provided in these visualizations. But if you do use a smaller data set for a different use case, then this pair plot can be a great tool. So with that out of the way, let's actually move on to the next visualization, which will be really helpful in our case. And it's going to be the distribution plot from Seaborn. So generally, you want to check the distribution of your target column since that's what we're trying to predict. And in our case, we're trying to predict the price of houses. So in order to get a distribution of the counts of these, to get a distribution of the values of these house prices, we can do this by passing in sns.diskplot df underscore Boston, and we're taking in the house prices column. So with this, we're going to see a distribution plot of all the house price values and the density or the count of these values. So as you can see, that it looks like the average price for the houses is falling somewhere around the 15,000 to 20,000 price point. So the data looks somewhat normally distributed in some areas, where it's more uneven in other areas. Like towards the end, it's getting more and more uneven with some more outliers. But the data looks somewhat normal, and generally it's good to have your targets be normally distributed, but that won't always be the case. So that's the disk plot. Another interesting visualization that you may want to do with your dataset is to create a heat map of the correlation between all the columns and features. So this I'll explain as I move on. It's a little bit harder to show you without visualizing it. Let's first start by actually producing a matrix of all the correlation values between our features. And we can do this by passing in df underscore Boston.core. So what this does is it's going to produce a matrix that shows you the correlation between all of your columns. So if we look at some of the corresponding columns, we can see how they're correlated and what are the numerical values that display the correlation. And that's the numerical way of representing it. We can then plot out these correlations using the heat map. So let's do this by saying sns.heatmap, and then we'll pass in that matrix. Let's run that. Great. So here we can see a diagonal of full correlation, and that makes sense because every column should be correlated with itself. The way you actually read this is you look at the column and see the corresponding column, and that's going to give you the correlation value. So the higher the number, the more correlated it is, the lower, the less correlated it is. So we can see that this diagonal is all 1.0 or 100%, and that's because every column should be correlated with itself. We can also see information and correlations between different columns and how they relate to each other as well. So to see these correlations numerically, we can put in anot equals true. So we're putting in this parameter to see not just the color, but also the numbers. In our case, it might be a little bit messy because of how many features we have. Yeah, so as you can see, it's a little bit messy. You can't really read it. So if you do have less features and a smaller data frame, then you'll probably be able to see the numbers more clearly. But that's something that you can definitely try out with a different data set. Now that we've gone over some of the basic EDA and visualizations, let's get started with the model training process. First, we'll need to split our data into X and Y arrays, and I'll show you what that means in a second. But before we do that, let's just do a quick recap of all of our columns to get familiar with them. And we can do this. We can grab all the column names by passing in df underscore Boston dot columns. Yeah, so as you can see, these are all our columns that are in our data set. Everything up until LStat is going to be feature columns, and the house underscore prices is going to be our target column or our dependent variable. So before we actually start doing the model training and doing the train test split, we have to first split our data into X and Y arrays. And what this means is the X array will only contain the feature columns or the independent variables that the model is going to train on, and the Y array will contain the target variable that the model will try to predict. And in this case, the Y array is only going to contain values in the house underscore prices column. So if I write this in code, we're going to say this X array is going to equal df underscore Boston dot drop. And by doing this, what's happening here is we're going to drop the column that we don't want in our array. So we're going to drop house underscore prices, and we're going to set axis equal to 1. And in the Y array, we want to only have the house underscore prices column since that's our target variable. So we'll say df underscore Boston house underscore prices. So by doing this, we're just getting the column. By doing this, we're taking everything except that target column. So we're basically having a data frame that contains all of our feature columns except the target column. Cool. So now that we've done that, let's run. Oh yeah, and also to note, this axis equals 1, essentially what this is doing is it's basically if you're going to make it permanent, and if you in order to actually drop for 2D structures like a data frame, you have to set axis equal to 1. Great. So now that that's done, we can actually start moving on to the model training process. Now that we have our features and target data split and set up, let's shift to using scikit-learn to actually train our machine learning, our linear regression model. The first thing we want to do is perform a train test split on our data. And we can do that by saying from sklearn.model underscore selection import train test split. So this train test split function, what it's basically doing is it's going to allow us to split our data into a training set to train and allow our model to learn from the data, and a test set to evaluate or validate our model once it's been trained. So to implement that, we're going to use this train test split function, train underscore test underscore split. And there's a lot of moving parts in this, so I'm going to go step by step. First, with the train test split function, what we're essentially going to do is we're going to pass in our X and Y data, and then we'll specify a test size. So that's going to be how much of our data is going to be used for testing and how much will be used for training. Let's first start by saying train test split X. We're going to pass in our X and Y data, and then we're going to set the test underscore size. Test underscore size equals 0.4, and random underscore state equals 101. And let me actually just finish writing the entire line of code, and then we'll break it down. So X underscore train, X underscore test, Y underscore train, Y underscore test. All right. So what we're doing here is, so let's first start off with so we already know that the X and Y arrays have been passed in. Let's explain what test size is, what it means and what it's doing. So test underscore size is essentially saying, like I said, it's going to specify how much of our data is going to be allocated to evaluating or testing our model. So by saying test underscore size equals 0.4, we're essentially saying that we want 40% of our data to be allocated to evaluating or testing our model. This means that if 40% is for testing, 60% will be used to train our model. And this ties in with what these variables are. So X underscore train and Y underscore train are going to be the feature data and the target data that's going to be used to train our model, because in supervised learning, we're going to need both the features and the target or label to train our model, since we're using labeled data to train the model. So that means 60% of these values, so 60% of features and 60% of the target column, are going to be used to train the model, and this x underscore test and y underscore test variables are the opposite. These are the feature columns and the target column that will be used to test and evaluate our model's performance in terms of detections, sorry, in terms of predictions. So those are what these variables stand for. And what the random state means is, so first of all, this random state parameter is optional. And what random state is doing is it essentially ensures a specific set of random splits on our data. And this is because train test split occurs randomly. In order to make sure that your random split is the same as my random split, you need to set it to 101. So that way we'll get around the same, so that way our results when we finish training our model will be the same. The model will be trained in the same way, and the data will be split in the same way. Another thing I want to mention is that test underscore size doesn't have to be 0.4. It can also be 0.3 and 0.2. Those percentages are also commonly used, but it's completely up to you on how much data you want to train your model with and how much you want to test the model with, and you can play around with that. For the sake of this walkthrough, I put 0.4, and if you want like the same results as my model, go with that as well. So now that we finished splitting our data and applying the train test split, let's now call in the linear regression model from scikit-learn. Let me first run these. Oops, I forgot spelling. There you go. All right, cool. So we got that. We'll run this cell. So now let's import our linear regression model from scikit-learn. So we'll say from sklearn.linear underscore model import linear regression. All right, so now that the linear regression model has been implemented, we now want to instantiate an instance of the linear regression model. So we're going to do that by saying lm equals linear regression. So if you're familiar with Java or object-oriented programming, this is basically like creating a linear regression object. So by saying lm equals linear regression, we have the model instantiated, and this lm is going to be our model. So we're now going to train our model using the fit function. So we're going to basically, as the name suggests, we're going to train or fit the linear regression model on our training data. So we'll do this by passing in lm.fit, and the parameters will be x underscore train and y underscore train. So when we run this, notice this message here. That's basically saying that the linear regression model has been trained on our data. So now that's done, we can start with the model evaluation. So the first thing that we can do to evaluate our model is checking its coefficients and seeing how we can interpret them. I'll go into what exactly the coefficient values mean and everything in a sec, but let's first call these values. So we can grab our coefficient values, but for each feature by saying lm.coef underscore. So if we run this, there. So these are the coefficient values for each feature. To explain this better, I'm going to convert these into a pandas data frame, and we can do this by saying CDF. So this stands for coefficient data frame is equal to PD dot data frame. So when we make this data frame, it's going to be a little bit different. I'll explain in a sec what we're going to pass in. So when we're creating a data frame for our coefficients, we're going to be passing in the coefficients as the data and our feature columns as the indexes. And we'll do this by saying pd.dataframe lm.coef, since that's our data, underscore. Then we'll say x.columns, since that's going to be the feature. The feature names will be the indexes of this data frame. And then we'll say the column will equal coef. And I'll show you what that looks like in a second after I run this. All right, so let's get a visual of this. We can say CDF. There you go. So this is what the coefficients data frame looks like. Like I said, the feature names are going to be the indexes, and then we're going to see their coefficient values on the right, and this will be the column. And now I'm going to explain to you how to interpret this data frame. So I'll do it with an example. Basically, let's take this Zn feature. Okay, so basically, if we hold all these other features fixed or constant for our model, what this coefficient value is saying is a 1 unit increase in the Zn feature is associated with an increase of 0.04 in the price. Or in other words, a $40 increase in price, since we have to multiply um, by 1,000, since the price of the houses will be in thousands of dollars. If we take another example, we will say, let's take the age. So the age features. So we can interpret it by saying a 1 unit increase in the age feature is associated with an increase of approximately $16 in the price of the house. If we take the tax feature, what we're saying is a 1 unit increase in this tax feature is going to result in an $11 decrease in the price of the house. So that's essentially what these coefficients are telling us by how our model has trained on the data set and how the line of best fit has fitted on our data. And that concludes this first part of the Python linear regression implementation. In the next video, we'll go over how to make predictions with our linear regression model, and we'll evaluate them as well. Thanks for watching, and I'll see you then.